sampling and rock core. Systematic rock sampling can be used to characterize a geothermal reservoir. The physical and chemical properties of rock samples provide important information for determining whether a power generation or heat utilization facility can be developed. Some general rock properties can be measured by visual inspection, but detailed properties require laboratory techniques. Apparatus. Number 1. Drilling rig with rotary power. Number 2. Hoisting systems. Number 3. Casing. Number 4. Rods. Number 5. Core barrels. And number 6. Pumps with a circulating system. Techniques for obtaining rock samples. 1. Sampling by drilling. Drilling methods and equipment shall be selected as a function of the required sampling category. The flushing medium should be selected to meet the requirements of the investigation, and if necessary, appropriate additives can be added to the flushing medium. Block sampling. In block sampling, samples are obtained from a trial pit, heading, shaft, or from the bottom of the borehole by using special samplers with cutting procedures. Integral sampling. In integral sampling, complete, oriented, and undisturbed core samples can be taken in order to preserve the rock mass characteristics, unattained by the drilling effects, in the core samples, and to determine the primary conditions of the natural discontinuities and their orientation. Rock samples. Number 1. Cores. Number 2. Cuttings and retained returns. Number 3. Block samples. Categories for rock sampling methods. 1. Category A sampling methods. By using Category A sampling methods, it is intended to obtain samples in which no or only slight disturbance of the rock structure has occurred during the sampling procedure of the sample. Examples: sampling by rotary core drilling using a triple tube core barrel. Sampling by wireline core drilling. Block sampling. Number 2. Category B sampling methods. By using Category B sampling methods, it is intended to obtain samples that contain all the constituents of the in situ rock mass in their original proportions, and the rock pieces have retained their strength and deformation properties, water content, density, and porosity. Examples: sampling by rotary dry core drilling. Sampling by rotary core drilling with either single or double tube core barrel. Integral sampling. Number 3. Category C sampling methods. By using Category C sampling methods, the structure of the rock mass and its discontinuities have been totally changed. The rock material may have been crushed. Some changes in constituents or in the chemical composition of the rock materials can occur. The rock type and its matrix, texture, and fabric can be identified. Examples: sampling of cuttings by rotary open hole drilling. Locating the groundwater table. To locate groundwater accurately and to determine the depth, quantity, and quality of the water, several techniques must be used, and the target area must be thoroughly tested and studied to identify hydrologic and geologic features important to the planning and management of the resource. Preliminary survey. It is highly advisable for phreatic layer investigators, especially if they are not from the region concerned, to carry out preliminary surveys in order to collect information which can give them precious data on the places where there is a likelihood of finding water. Dowsing procedure. Choosing a forked or Y-shaped twig from a tree such as a mango tree, or using metal rods. Positioning the twig or rods between the fingers so as to amplify the sensations felt, and seeing if they twitch and go down or cross at the expected place. Crisscrossing the area in order to determine the most promising areas. Modern methods. Topography. Analyzing maps and local vegetation gives a first indication of the presence of water. Hydrogeophysics. Geophysical methods are now the main methods of investigation and detection of underground aquifers. The isotope method. This method is mainly useful for tracing the water flow and to estimate the age of the groundwater.
Number and depths of boring. There are no clear-cut criteria for determining directly the number and depth of borings or probings required on a project in advance of some subsurface exploration. Number of boring. For buildings, a minimum of 3 borings where the surface is level and the 2 borings indicate the regular satisfaction may be adequate. 5 borings are generally preferable at buildings, corners, and centers, especially if the site is not level. On the other hand, 1 boring may be sufficient for an antenna or industrial process tower based in a fixed location with a hole made at the point. 4 to 5 borings are sufficient if the site soil is non-uniform. Depth of boring. Borings should extend below the depth where the stress increase from the foundation load is significant. This value is often taken as 10% of the contact stress scope. For the square footing of the vertical pressure profile shows this depth to be around 2b. Since footing sizes are seldom known in advance of the borings, a general rule of thumb is 2 times the least lateral plan dimensions of the building, or 10 meters below the lowest building elevation. Where the 2 times width is not practical as, say, for a 1-story warehouse or a department store, boring depths of 6 to 15 meters may be adequate. On the other hand, for important or high-rise structures that have small plan dimensions, it is common to extend 1 or more of the borings to bedrock or to competent soil regardless of depth. Geotechnical report. The report should be as clear, concise, and accurate. Both an adequate site investigation and a comprehensive geotechnical report are necessary to construct a safe, cost-effective project. Engineers need these reports to conduct an adequate review of geotechnical-related features, for example, earthwork and foundations. The state-of-the-art consultant should prepare preliminary geotechnical reports for submittal to the design team whenever this information will benefit the design progress. Early submittal of the geotechnical information and recommendations or engineering evaluation of preliminary data may be necessary to establish basic design concepts or design criteria. This is commonly the case on large projects or projects containing complex or difficult geotechnical problems, where alignment and/or grade changes may be appropriate based on geotechnical recommendations. The development of a final geotechnical report will not normally be completed until design has progressed to this point where specific recommendations can be made for all the geotechnical aspects of the work. Final alignment, grade, and geometry will usually have been selected prior to issuance of the final geotechnical report. While the geotechnical report content and format will vary by project size and highway agency, all geotechnical reports should contain certain basic essential information, including summary of all subsurface exploration data, including subsurface soil profile, exploration logs, laboratory or in situ test results, and groundwater information, interpretation and analysis of the subsurface data, specific engineering recommendations for design, discussion of conditions for solution of anticipated problems, and recommendation. Heavy equipment used in soil exploration: auger boring machine, rotary drilling, percussion drilling, excavator.